Morning, everybody. I'm just going to introduce this particular task to you. This task will take you about an hour to do, I reckon, or at least to do properly. I'm going to demonstrate it, and I'd like you to have a go at it. Well, your submissible will be to copy and paste the graph and the table from your practical onto a Word document to show me what you've done. Okay, this is a compulsory practical. It is a useful one to do, as you probably guessed. The projectiles topic is one for which you often get asked a lot of practical questions, like whether or not to involve air resistance. So in the last lesson, we looked at projectiles, and those of you engaged with the Seneca task have shown me that you've understood it. So we're going to move on to a practical lesson today, and then we'll do some exam practice tomorrow. So if I look very, very carefully at my at the task I'm setting you today, it's on a little bit of a go slow, bear with me, it's gone a bit wrong. So we've obviously logging into the Zoom meeting, 11:15 was the start of the lesson, and you're going to use a simulation to do an assessed practical, and that assessed practical is in the description of it is on the sheet that you can also download to read as well. So, but what we're doing is you're looking for an optimum. Oh, sorry, I haven't shared my screen. I do apologise. Try that again. So in your show my homework, you've got a practical which is due tomorrow. So it's to do today. So you've got a little bit of a simulation here with. Bear with me. Get to that. You've got a simulation to have a go at, which is the link for it is here. It's also in the Word document for you to download, which describes the task to you. I'm going to show you anyway how to do this. So we're going to be going on to a projectiles simulation, which is here. And the particular module you want is the lab module. So if I click on the lab module, you've got a cannon here, which fires projectiles, which land some distance away, and you probably want to zoom out a little bit so that you can measure the distance. And we're going to have a high initial speed of 30 meters per second. So that's something to remember. So when you fire a projectile, remember that it is just acting under gravity. At the moment, I've got my air resistance switched off. So we're not really bothering about air resistance for the first part. And then the second part, we're going to look at air resistance in a bit more detail. As you may notice, when you fire a projectile at a particular angle, it follows that parabolic path that we talked about yesterday. And because the only thing really affecting this is gravity, the thing to remember is that it doesn't matter what it is when we've not got any air resistance. So over here I've got a cannonball. It could be a pumpkin. Follows exactly the same path. It could be a car, or a piano. It follows the same path, so it doesn't matter what it is on this first experiment. So what we're doing is we're looking at the relationship between the launch angle and the distance or the range. Okay, now when you look at the launch angle, you can adjust it just by dragging and dropping. This works also by touch screen on your phones and tablets, so it's quite a fun one to do. So all we're doing is we're looking at the range. So my minimum sort of launch angle is 25 degrees. As I fire my cannonball, it travels a set distance, which you can measure using a measuring tape. I'll put my cross from the back of my tape there. I can stretch my tape out, and I can measure my distance, 70.28 meters. Now, when we're recording that, you want to use a table. Now, as we've got opportunity to be online, you can just record it on a paper table and take a photo of it, draw a graph manually using some graph paper if you happen to have some, or you can use Excel. So I'm going to allow you to either use a hand-drawn set of graphs and tables, or use an Excel spreadsheet to draw your graphs for you. So I'm going to use an Excel spreadsheet and just show you. So I'm just going to move that across. There we are. Now, I'm just going to hide that bit for a moment because we're not using that just yet. Now, my distance was 70.28 meters. So I could just put that in a table here. So I've got my launch angle on my left side, my distance traveled, 70.28 meters, okay? And then all you do is you adjust the launch angle, say 25, maybe 35, measure with your tape measure, and so on, putting that into the table. So I've actually previously already done it. So here's one I prepared earlier. So I've got my launch angle and my range, because we're looking to find out what launch angle gives you the optimum range. Now, you know that theoretically, we said 45 degrees gives you your optimum range. So we're looking more precisely between sort of 40 and 50, but we're looking at the outside regions because we like to get a good range anyway. But we're not that bothered about the about these extremes. So we've got a 10-degree difference here. As we get closer to what we predict would be the optimum range, we want to make our readings a bit closer together. Then all you have to do is draw a graph. Now, you can draw a graph on graph paper, but what you can do is if you select on Excel, you go to Insert, and you could draw your graph. Now, you're looking for a chart, which is a scatter. So it's this one with the little dots in it. So click on that. All I want is a scatter with a line on it. There we are. And you can actually see what your scatter looks like. Now, here you can tell straight away the optimum range was definitely at 45 degrees. So there's your first part of your conclusion. But the extension on the worksheet also then asks you to look at air resistance. So if I clear that, I'm now going to redo my experiment. Just going to move those out of the way. Redo my experiment, but this time at my selection of angles, but I'm going to take into account air resistance. And when I take into account air resistance, I can start to think about sort of drag coefficients. I can think about sort of what I think the drag coefficient would be, but I would want something where the drag coefficient is going to be quite high. So something like a baseball. If I click on something like a baseball, I can actually then work out what the drag coefficient is. You can even, if you want to, do something that's customized, and you can set your own drag coefficient, maybe to 1.0, for example, and that gives you more drag. But I'm just going to use something like a baseball for now. Okay, I'm at 0 altitude to create the most friction, because I want to see what effect the air resistance has on the optimum launch angle. So I could fire my baseball, my initial speed of 30 meters per second. I'm keeping that constant, and I just fire it. Now you could see that it looks pretty much the same, but the difference occurs when you're looking at what that range is. Now, at 25 degrees with air resistance, it's 55.77 meters. So if we look on our graph, we could see at 25 degrees, it was actually a lot more. So the air resistance already has an effect on the graph. Now, I've taken my readings, and I've found I've got a graph that looks a little bit like this, a table or a set of results that looks a little bit like this, where I've got from 25 to 65. Well, my optimum here previously was 45 degrees, but when I measured at 40 degrees, it was about the same. So my optimum is probably my optimum launch angle here is probably somewhere in between these two. So what you then do is you take readings in between here to find out where the peak is. So there, I've done it. It's almost like I planned ahead. So I've got my my readings at 1 degree intervals between 40 and 45 degrees, and that gives me a better set of results. That gives me a set of results where I've taken more readings at the area that I'm actually really interested in. So we're then drawing the same graph. Insert, scatter graph with a line of best width. I'm not going to do the line of best fit because it doesn't really draw it terribly well. So I'm just going to draw it with the dots. And I'm going to show you what you can do to find the optimum launch angle. I'm going to expand my graph so you can see it clearly. And what I need to do is to add a trend line. So I right click on one of the dots and I want to add a trend line. And what I'm looking for is a polynomial trend line, okay? Because we're expecting a parabola. And that gives me a polynomial trend line. Now, I'm not really, when it looks for the optimum angle, well, it looks like it's somewhere around about here, but I want to be a little bit more precise. So you can right click on your axis and you can add the minor grid lines to start off with. And you've now got some minor grid lines in here, makes it easier to take readings. And here we've got lots of wasted graph paper space. So what I want to do really is just change my axes so that my minimum on my y-axis, well, I've not got anything below about, range below about 50, and I've not got anything above 70. So my minimum here really shouldn't be 0, should be about 50 meters. And my maximum is about, well, here it's 68. So I'm going to say 68. You can actually then start to see exactly where your peak is. The peak is about here. So when I actually read it down, for me, well, these are 2, so it's 42.5 degrees, not 45 degrees. So that's the practical I'd like to have a go at doing. Once you've done the practical and you've taken your readings, drawn your graphs, what you can do is then use the use the simulation to have a few, to have a little bit of a play. You can see what difference it makes, for example, to your optimum if you increase the air resistance. You can see what happens to the you can see what happens. Okay, so your first major task really is to have a go at the compulsory practical. The compulsory practical, as I said before, the description of the task is here. This video, which I will be posting on as a recording, as I don't seem to have many people joining us at the moment, so we're almost done. I'll be posting the recording of this lesson on YouTube and on WeTransfer for those of you who can't access YouTube from your home countries. And what you can then do is watch the demonstration and then have a go at it. Okay, so but your key is the 2 things you need from here, from your task on Show My Homework, are the practice description of the required practical on the download, and this link which will take you to your simulation. And remember, on the simulation, you are looking, you get into your home screen there, you're looking at the lab, you're changing your angle, your launch angle, keeping the initial speed high at 30 meters per second, and you're measuring your range using the tape measure, which starts off up in this box. Okay, any questions? Any questions? Okay, I'll stop there then. And what I'll do is I will come out of the meeting, I'll end the meeting, but then I'll re-enter the meeting so that if you do have any other questions, you can come back into the meeting and you can ask me anything that you need to ask me, okay? I hope you enjoy the practical. It is meant to be quite a lot of fun, and I'm sure you'll find it very informative as well, okay?